Hello, this lesson is from page 130 in your book, and the objective is that student will be able to estimate square roots of non-perfect squares. And that just means you'll find the two squares on either side of the number that's not a perfect square, and you'll see which one's closest. You'll do fine. So what steps do I take to estimate the nearest square root of a non-perfect square root? All right, so first of all, this helps me quite a bit, and so I would like you to take a minute and just copy down a number line. I want your number line to go, it's easier from 0 to 100, and then down here you can just have 110 up to about 200. You can stop. But let's talk about it first, and then you can pause and then copy this part down. So here I've made the number line, and 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81. Notice how as the base gets larger, because you're multiplying it times itself, the perfect squares are more spread out. And then 10 squared is 100. Then here, 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. So yes, I would like you to have these two number lines in your notes. All right, so in your book today, they will just give you just this part, the square root of 83, and they'll ask you to estimate, is it closer to the square root of, 81, the square root of 81, which we already know is 9 times 9, or is it closer to the square root of 100, and that's 10 times 10. Just to let you know, they won't give you the 81 and the 100. You'll have to first think, oh, 83 is between 81 and 100, the two perfect squares that is in between. And then your second step, you'll change the perfect squares to square roots. And so 9 times 9 is 81, and I put that on the number line. And 81 and 83 are very close together. And then 10 times 10 is 100. And so you would say, to estimate the nearest perfect square to the square root of 83 is 81, because they were closer. So 83 is closest to the perfect square of 9. All right, so here's all you will see in your book. And they'll say, estimate to find the nearest perfect square to 52. So you will think, what perfect square is a little less than 52? And what perfect square is a little more than 52? So right away I thought, oh, 7 times 7 is 49. And 8 times 8 is 64. So those are the two perfect squares that the square root of 52 will fall in between. So then my second step is to think, oh, well, that's in between 7 squared and 8 squared. And then I have my number line, and I think, oh, 49 and 52 are only 3 numbers apart, but 52 and 65 are 13 numbers apart. And so, oops, I don't want that. So the square root of 52 is closest to the square root 7. I hope that makes sense. Oh, I forgot to cover these up. All right, that's all right. So the next one, the square root of 170, you think, oh, it's in between the perfect square 169. That's why you have that number line from the very first objective slide. And the next largest perfect square is 196. And so we know that's 13 squared and 14 squared. And you'd think, oh, look, here they're only 1 apart, so I didn't even bother to make the number line. And you don't have to make a number line either. If you can tell right away it's closer. Here they're only 1 apart, and here they're 26 apart. So 13 is the closest square root to 170. We'll save those for in class. All right, so there was an example in your book that I found very fascinating, and it's on page 131. So if you have your books open, the real world example talks about a golden rectangle. It's like a ratio that when they create a spiral pattern in nature and they create the ratio of the length to the width, this is the ratio that you see here. 1 plus the square root of 5 divided by 2. They're saying this is a pattern, a ratio, repeated frequently in nature. I thought that was really interesting. So you would estimate, when you see this, don't let it stump you, you'd estimate the square root of 5 is closest to 2, right? 2 times 2 is 4, so that's pretty close. So you would estimate and think, oh, well, 1 plus 2 is 3 over 2. And then if you want to reduce that one more step, it'd be 1.5. But I would accept it this way, or 1.5, or 1.5. All right, the next one is check your progress on page 131 in your book. And I'll read it just a second. It says, in a Little League, the bases are squares with the sides 14 inches. The expression, the square root of s squared plus s squared, meaning the 2 sides, represents the distance diagonally. And so I just drew a quick little baseball diamond. And they're saying if each side is 14 feet, what is the middle distance? And they're saying, oh, the middle distance is side squared plus side squared. So right away, you would fill in, oh, 14 squared plus 14 squared is 196 plus 196, and the square root of that, oops, is the square root of 392. Oops, oh, let me pause a minute. All right, and I know your number line went as far as 200, but we didn't keep going. So you would actually have to use a calculator to say, oh, which perfect square is 392 closest to? And 20 times 20 is 400, which is very close. So you would say, estimating the length of the diagonal across the baseball field for the Little League is about 20 feet. And so they gave us the formula. We just plugged in the 2 sides, squared them, added them, and then found the square root. And what is it closest to? And you would say 20. You could also, with your calculator, just find the square root of 392. And obviously, if it has a decimal of 0.5 or greater, you know it, you'd round it up. So that's an option also. Oops, just a second. Won't let me advance. There we go. All right, this is from page 43. I'm sorry, number 43 from page 133. And it talked about having a container that is 4 cubic feet. Will it fit on a shelf that's 12 inches tall? And so you would think, oh, cubic right away means the cubic root of 4 means the length times the width times the height. And if this is my container and it holds 4 cubic feet, what must each side be? Because my volume is 4 cubic feet. So right away, I just went on my calculator and I said cubic, the cubic root of 4 was 1.4 587, and it was a longer decimal than that. And so I thought, oh, that's a little over or 1.5 feet each way. Does that make sense? So this side is over 1.5 feet. Whoops. Boy, it just won't let me unclick. There we go. This side is over 1.5 feet, and this side is over 1.5 feet. And so 1 foot is 12 inches. And so to fit on the shelf, it would have had to be 12 inches or less. So it is too big. It will not fit on the shelf. And that's it for this lesson. It isn't as hard, but sometimes those real examples are hard to apply. Now, what are they really asking? So we'll work on those together in class. Have a great night.